Okay, hello everyone in a new video. In this one, we are going to explain chapter 1 in the first unit, which is the unit of optics. The title of this chapter is lenses. In this chapter, we are going to introduce the lens and distinguish between different type of lenses according to their shape and how do they affect light. For this, let's start by defining a lens. Then section 1.1 definition. A thin lens is a transparent and homogeneous medium of small thickness. Then what does the word transparent means? Transparent means that when we look through the lens, we can see what's found behind the lens. Okay? And the word homogeneous means that it's made up of the same material. Usually, lenses are either made up of glass or plastic. Okay? If the lens or if the medium is made up of a mixture of both plastic and glass, then this medium is not lens anymore. The lens is either made up of glass or plastic, limited by two surfaces called the faces of the lens. One of these faces at least is spherical, while the other face is spherical or plane. Here, if you look at the first figure here, we can notice that this is a lens because it is transparent. We can see what is found behind the lens, and it is homogeneous because it's obvious that it's made up of glass. Here on the right we have three lenses. This is the first lens. These are the faces of the lens. In this case, both of them are spherical. Now if we look at the second lens, the first face here is straight. So this is a plane surface, plane face. This is plane, while the other face is spherical. And if we look at the third lens, both faces of the lens are spherical. Okay? So by this, the faces of the lens, one of the faces at least is spherical, while the other face is spherical or plane. Okay, so this is the definition of the lens. Now we come to the more important question, which is where do we use lenses in our daily life? Here are some uses of lenses. Okay, so let's check them out. So the first one is a lens of a camera. Nowadays, cameras in smartphones are very important, and whenever we need to buy a smartphone, the first thing we look at is the camera. So the camera is made up of a lens. Let's see another example. A lens of a photocopier. Now this example is not trivial, but indeed inside of a photocopier there is a lens which allows to collect the image of the paper, as we can see here in this figure. Okay, so this figure is what's happening inside the photocopier. Also, the lens of a projector that is used at home and theaters, which allows to project the image on a screen. In this case, it is the wall. A magnifier are also made up of lenses through which we see a magnified image of the text. As we can see here in the animation, we are observing a magnified image of the text. Finally, the lens of a peep door viewer. So we all know that lenses are installed inside the door. Now this example is extremely important because this lens allows us to see a wide view of what is behind the door. At the same time, the person standing behind the door cannot see what is inside the house. Okay? There are several more examples about the uses of the lenses, like the eyeglasses that we wear and the telescope, microscopes, etc. But now we come to the question that are all the lenses the same? For example, the lens here that is inside the camera, is it the same as the lens inside of a peep door viewer? Actually, no. Mainly there are two types of lenses. So by this we have reached section 1.3. What are the type of lenses? There are two types of lenses. The first one is a converging lens. The converging lens is thicker at the center and thinner at the edges. Here we have some types of converging lenses, or some example of converging lenses. A converging lens is thicker at the center and thinner at the edges, and this is known as biconvex. This is a converging lens because it's thicker at the center and thinner at the edges. This is convex concave. And another example of a converging lens is the plano-convex. It is thicker at the center and thinner at the edges. For this reason, we call a converging lens a thin edge lens. It is thicker at the center and thinner at the edges. The other type of the lens is a diverging lens. It is thicker at the edges and thinner at the center. Notice that this lens is thicker at the edges and thinner at the edges, so it is a diverging lens. Also, this is known as biconcave. This is thicker at the edges and thinner at the center. This is also a diverging lens. The same for this, it is thicker at the edges and thinner at the center, and this is known as plano-concave. Okay, but notice that here we have a problem. These shapes are hard to draw each time. So it is hard to draw these shapes each time we need to use them. Okay, so we will use a well-known trick in physics, which is drawing using symbols. Then let's give a symbol for a converging lens and for the diverging lens. Then section 1.4, symbol of lens. We will give the converging lens the following symbol. Why? Because if you complete this symbol, we will notice that it is thicker at the center and thinner at the edges. As for the diverging lens, we will give it this symbol. Why? Because if we complete this symbol, we can notice it is thicker at the edges and thinner at the center. Okay, and now after we gave a symbol for each type, we are ready to represent a lens in an optical system and check how does it affect a ray of light, which allows us then to study the properties of a lens. Then the next section will be the optical system of a converging lens. Okay, now let's move to the second section. Section number 2, optical system of a converging lens. Let me write it down. Section number 2, optical system of a converging lens. Then now, after we have learned the symbol of a converging lens, we need to learn how to represent a converging lens in an optical system and check how does it affect a ray of light, which allows us to study the properties of a converging lens. Okay, so let's consider that the direction of propagation of light is from left to right like this. So this arrow indicates the direction of propagation of light from left to right. Then light is only allowed to travel from left to right. This is the direction of propagation of light. As a first step, we always start by drawing the optical axis. In the same direction of that of propagation of light. I repeat, because the direction of propagation of light is from left to right, we draw the optical axis in the same direction from left to right. This is the optical axis. okay, x prime x. Then let's write idea number 1. X prime x is the optical axis of the lens L. Okay, so where is the lens L? We place the lens L perpendicular to the optical axis at the center. This is the lens L. And because we are constructing the optical system of a converging lens and we have learned how to represent a converging lens using symbols, we use its correct symbol. This is the symbol of a converging lens. This is the lens L. Then let's write idea number 2. L is a converging lens. The point of intersection between the optical axis and the lens L, we will name it to be the point O, and O is known as the optical center. O is the optical center. Why O is the optical center? Because it is the intersection between the optical axis and the lens L. Therefore, whenever they ask us why O is the optical center, the answer would be because it's the intersection between the optical axis and the lens L. So this statement is very important, okay? Now we come to the fact that not all converging lenses are the same. Then what distinguishes one from the other is the focal length. However, in order to define the focal length, first I must introduce the object focus and the image focus. Let's say that f is the object focus and f prime is the image focus. Because the direction of propagation is from left to right, and the lens that I'm using here is a converging lens, we always place the object focus to be on the left and the image focus to be on the right. Okay, I repeat, because the direction of propagation of light is from left to right and the lens that I'm using is a converging lens, then the object focus will be on the left and the image focus will be on the right. Okay, suppose here that if I have taken the direction of light to be from right to left, this is the optical axis like this. Because the direction of propagation is from right to left, then I take the direction of the optical axis in the same direction of that of the light. I place the lens L perpendicular to the optical axis. Okay, then the object focus will be on the right and the image focus will be on the left. Moreover, notice here that I have placed f and f prime in such a way that they are separated by the same distance from O. And this is an important statement. We say that f and f prime are symmetric with respect to O. Okay, so they are separated from the same distance from the optical center, by the same distance from the optical center. So whenever we know the position of either of them, for example, if we know the position of the object focus, we can directly deduce the position of the image focus because it's the symmetric of f with respect to O. Now we are able to define the focal length. What is the focal length? So idea 4.2, the focal length denoted by small f and not capital F. Usually we use capital letter for the object focus and the image focus, and a small letter for the focal length. The focal length is equal to OF prime bar, the distance from the optical center to the image focus is the distance from the optical center to the image focus. Let's say here from the optical center O to the image focus F prime. Okay, so what does the focal length represent? Focal length is the distance from the optical center to the image focus. Then this is the focal length. This is the distance from the optical center to the image focus. Okay, this is the focal length. So in this case, it is a 3 divisions. But now the question that we need to answer is that what does the bar over OF prime represent? Okay, F is equal to OF prime bar. Now this bar, notice that this is a bar and not a vector. It's not a vector, it's a bar. This bar over OF prime means that this distance, the focal length, may be positive or negative depending whether we are measuring the distance along with the same direction of the positive x-axis or in an opposite direction of the opposite axis of the x-axis. Here F, the focal length, is equal to OF prime bar, which is the distance from the optical center to the image focus, which is in the same direction of the positive x-axis. Because it is in the same direction of the positive x-axis, then the focal length is positive, and this is another property of a converging lens. Then 4.3, for a converging lens, the focal length is positive. Okay, now one could say the following: because the distance OF prime is equal to the distance OF, we can simply define the focal length to be F is equal to OF bar. But now, according to this definition, the focal length is the distance from O to F, which is in an opposite direction of the positive x-axis, and by this now the focal length is negative and not positive. And this is wrong, because we know that for a converging lens the focal length is positive. Okay, now it's left to represent how does a ray of light crosses the lens. So because the direction of propagation of light is from left to right, let's consider a ray of light passing through the lens. This is a ray of light. It hits the lens and emerges from the lens. Let me label some stuff. This is the point A and this is the point I. Then the ray is hitting the lens at the point I and emerges along IR. These arrows that I have drawn here indicate the direction of propagation of light, which is from left to right. Okay, so whenever in optics, whenever we need to draw a ray of light, we need to draw on this ray arrows like this that indicate the direction of propagation of light, which means that light is traveling or propagating from left to right. Okay, let's say the following: AI is an incident luminous ray, and IR is the emergent ray. Then what does the word incident means? Incident means hitting the lens. And the word luminous means made up of light. Okay, I repeat, the word incident means it's hitting the lens, and the word luminous means made up of light. As you can notice here that the ray II is hitting the lens. For this reason we call the ray AI an incident luminous ray. Incident because it's hitting the lens, and luminous because it's made up of light. Whereas the word, let me here write, emergent luminous ray, the word emergent means coming out, and the word luminous means it's made up of light. As you can notice here that the ray IR is coming out from the lens. For this reason we call it an emergent ray, emergent luminous ray. Okay, moreover here notice that I have drawn the ray IR coming out from the lens toward the optical axis. If I complete the incident ray II like this, dotted, we can see that the ray IR is emerging toward the optical axis and not away. And this is another property for a converging lens. Let me write it down here. .1, the emergent ray emerges from a converging lens toward the optical axis. So this is the effect of the lens on a ray of light of a converging lens. Now finally let's add some more properties for a converging lens. Moreover, the side where the incident ray is found, here we call it in front of the lens, and the side where the emergent ray is found we call it behind the lens. I repeat, the side where the incident ray is found we call it in front of the lens, and the side where the emergent ray is found we call it behind the lens. Then anything that's found here is said to be in front of the lens, and anything that's found here will be behind the lens. For example, the object focus f is in front of the lens, the image focus f prime is behind the lens. Now notice that here for a converging lens the incident ray and the object focus are on the same side. Let's write it down. This is another property of a converging lens, 5.2. For a converging lens, the incident ray and the object focus are on the same side, whereas the emergent ray and the image focus are on the same side. And by this we have finished the construction of the optical system of a converging lens. Let's repeat what are the properties of a converging lens. So the first one is that the focal length for a converging lens, the focal length is positive. This is the first property. The second property is that the emergent ray emerges from a converging lens toward the optical axis. The third property is that the incident ray and the object focus are on the same side. And the fourth property is the emergent ray and the image focus are also on the same side. Okay, so the same analysis will be repeated for the optical system of a diverging lens in the next section. Then section 3, optical system of a diverging lens. We will repeat exactly the same steps as I have said. Therefore, we will first consider the direction of propagation of light to be from left to right. And by this we place the optical axis at the center, having the direction of of propagation of light in the same direction. So this is the optical axis x prime x. Therefore idea number 1 is the same. X prime x is the optical axis of the lens L. Where is the lens L? Here the lens L we are using is a diverging lens. Then we use the correct symbol of a diverging lens perpendicular to the optical axis. This is the symbol of a diverging lens. Okay. Then idea number 2, L is a diverging lens. And the point of intersection between the optical axis and the lens is O. Then O is the optical center. Why? Because it is the intersection between the optical axis and the lens L. Till now nothing is different except for the symbol. Now we need to introduce the object focus and the image focus in order to define the focal length. Then let F be the object focus. F is the object focus. And F prime is the image focus. Now here we will start to see some difference compared to the converging lens. First of all, because the direction of propagation is from left to right and the lens that I'm using is a diverging lens and not a converging lens, then we will place the image focus on the left and the object focus on the right. I repeat, because the lens here that I'm using is a diverging lens and the direction of propagation is from the left to right, then I place the image focus on the left and the object focus on the right. For example, if you consider the direction of propagation to be from right to left, and this is the diverging lens, then the image focus will be here and the object focus will be here. The image focus will be on the right and the object focus will be on the left. And similar to the converging lens, I have placed the image focus and the object focus in such a way that they are separated by the same distance, and this is known as that f and f prime are symmetric with respect to O with respect with respect to O better. Okay, now let's define the focal length. The focal length which is given by f is equal to O f prime bar. The definition of the focal length doesn't change and is independent of the nature of the lens, is the distance from the optical center to the image focus f prime. Then here the definition of the focal length is f is equal to O f prime bar. The bar means that the distance may be positive or negative. Notice that f is equal to f prime bar, which is the distance from the optical center to the image focus, and in this case this distance is an opposite direction of the positive x-axis. Therefore the focal length of a diverging lens is negative and not positive, and this is a property which distinguishes a diverging lens from a converging lens. So 4.3 for a diverging lens the focal length is negative. And now it's left to represent how does a diverging lens affect a ray of light. Let's draw a ray of light like this. This is an incident luminous ray and this is its emergent ray, and we don't forget arrows on light rays. Okay, let me label some stuff. This is the point A, this is the point I, and this is the point R. Then we call AI an incident luminous ray because the word incident means hitting the lens and the ray AI is hitting the lens. And IR is the emergent ray because the word emergent means coming out from. Then idea number 5, AI is an incident luminous ray and IR is the emergent luminous ray. Five point one. As you can notice here that I have drawn the emergent ray in such a way. If I complete the incident ray to be dotted, we can notice that I have drawn the emergent ray in such a way that it's emerging away from the optical axis, coming out away from the optical axis, and this is an important property for a diverging lens. Five point one for a let's say the following: the emergent ray emerges from a diverging lens away from the optical axis and finally the two more properties of a diverging lens. In the case of a converging lens, we have seen that the incident ray and the object focus are on the same side, whereas the emergent ray and the image focus are on the same side. In the case of a diverging lens, this will be the opposite. The incident ray and the image focus are on the same side for a diverging lens. The incident ray and the image focus are on the same side. And we call this side to be in front of the lens. Then anything that's found here is said to be in front of the lens, and we call this side to be behind the lens. Then behind the lens we have that the emergent ray and the object focus are on the same side, and this is the final property in this section for a diverging lens. 5.3 for a diverging lens. The emergent ray and the object focus are on the same side. Okay, so that's it for this section. We have seen 4 important properties of a diverging lens. The first one is that the focal length of a diverging lens is negative. The second one, the emergent ray emerges from a diverging lens away from the optical axis and not toward, which is the case of a converging lens. And finally, the incident ray and the image focus are on the same side, and the emergent ray and the object focus are on the same side. So that's it for me in this video, guys. In part 2 we will complete the explanation of this chapter.